I'm Hans Gellersen. I'm from Lancaster University. First author of this work is Diako Mardanbegi, who unfortunately can't be here because he's between jobs. And our collaborators were visiting students from Munich. So EyeSeeThrough, in a nutshell, is an object manipulation technique designed for 3D user interfaces. It is based on movable menus that can be brought into the line of sight so to align a tool over an object to manipulate. And gaze is used implicitly to determine which action to apply on the target object. Here you can see it in action, brief demo of it. We have a menu that is attached to the manual controller, and it can be moved over objects in the environment. Here, for example, to manipulate the light, dim it, or increase the lighting. So you see the principle. We have 2 pointers here, one to control a menu, and the other one to do the selection of the tool and the object by aligning them. So this idea of using visual alignment for selection goes back to the tool glass that was introduced in '93 for desktop interaction. So here you see the tool glass technique at work. The idea of a tool glass is to have a transparent menu that can be slid over your work surface. The menu in this case is a color palette, and it can be moved over objects with then the second pointer, the primary pointer, coming in to punch through the menu to the object, thereby selecting at once the tool and the object, the action and the object. Kabash, Buxton, and Sellen studied the tool glass in '94. They did the baseline comparison of how this works in comparison with the standard selection of either first the tool and then the object, or the other way around, first selecting a tool and then the object. And what they found is that the alignment performed better. In some ways, that's predictable because there's one motor operation saved. We have still 2 movements, 2 pointing movements, but only 1 click. On the other hand, there's a trade-off here. The 2 movements that are involved need to be well coordinated so that the technique works well. In the tool glass, this is achieved with mapping the interaction to both hands, and it matches the natural coordination, natural use of hands, where the non-preferred hand is very good at providing the frame of reference for the dominant hand. So the non-preferred hand in the tool glass moves the menu, puts it in place, and the dominant hand that has higher accuracy then comes in and punches through a tool to apply it on an object. So what we can take away from this study is that alignment can be more efficient as a selection technique, but it depends on the quality of the coordination of the movement modalities. So back to our technique. So in our technique, gaze is the primary pointer, and it is used with either head or hand as secondary pointer. So head and hand control the menu, and gaze performs the selection of the tool through the menu to the object. Yeah, we also need a click modality here, some form of confirmation of the visual alignment that the user can use, but any click method can be used. It can be dwell time or manual trigger. That doesn't affect the technique as such. So we've designed 2 variants of this technique. One in which the menu is attached to the head, so it's a kind of cockpit menu that moves with the head. And the other variant uses a handheld palette, as you already saw in the little demo clip. So in the case of the handheld palette, the hand is used to move the menu so that tools become aligned over target objects. And in the case of the cockpit menu, it's the targets gets fixated, and then head movement is used to move a tool into the visual line. So in evaluating our techniques, we had 2 goals. The first one was a comparison of our technique against 2-step selection as a baseline. So essentially doing the same as Kabash et al. Did for the tool glass, but we're doing it here for gaze selection. So we're comparing visual alignment and versus two-step gaze acquisition of tool and then object. The second goal here is a comparison of our two variants of how our technique performs with coupling with the hand versus head. Quick run through the study design. We had 12 participants, 2x2 conditions, so for the two selection methods, standard gaze acquisition in 2 steps versus the visual alignment method, and then 2 types of menus, so using head versus hand. We used a coloring task as similar to what you saw for the tool glass. The head-attached menu was presented at a depth of 60 centimeters in the scene, and the options were aligned so that on a radius of 20 degrees from the head center. We used the same menu layout also for the hand, but for the hand, of course, we didn't control depth. It depended on how users manipulated the menu. The procedure, we had 80 trials for each condition in 2 blocks. We used 2 blocks to also calibrate, again, in between to ensure that we have no confounds from eye tracking inaccuracies. And the conditions were counterbalanced. Our measures were selection time, task complete time, and user feedback. Brief look at the conditions. If you first look on the left here, you see our technique at work. This is for the cockpit menu, the head-centered menu. As you can see, we are always only showing one option on the target because we didn't want to have any confound from search. And it's a very simple alignment task on the left. The red line indicates the line of sight, so users keep their gaze on the central target, and when a tool pops up, then they move their head, rotate their head to bring it into the visual line. If you look at the little camera there indicating the eye line, you see that the line of sight moves, but that's purely the counter rotation of the eye when the head turns. And on the right, the baseline technique is always a 2-step gaze acquisition of targets. So you only see the eyes moving and the head is still. Here are our results. So we saw that our technique, EyeSeeThrough, was significantly faster than the 2-step selection. And we also found that the hand was significantly faster than the head for this task. User-reported results. Users found EyeSeeThrough requiring significantly more physical effort. That's obvious because the 2-step selection is simply two small eye movements, whereas the 2 variants of our techniques require either a good amount of hand movement, arm movement, or head rotation. Nonetheless, in spite of the added physical effort, 9 out of 12 users preferred EyeSeeThrough, and comments also indicated that this method of aligning was perceived as very natural, and users also commented that it allowed them to keep the gaze focus on one target, so this indicates that this is usable without attention shifts, which is the original idea of the tool glass, that we don't have to switch attention between tool and object by bringing them together. In talking about the original tool glass work, I stressed very much how important the natural coordination between the pointing modalities is. And here in our techniques, in both versions, we see a natural coordination of gaze, in one case with the head, and in the other case with the hand. So for eye-hand coordination, for alignment, it's natural that usually users look ahead to a target, so they have an object-oriented strategy in acquiring targets. And the moving object would then follow and arrive in the line of sight to be selectable. But some users also have, not in our study, but it's known from other work, have an action-oriented focus where they rather follow the moving object to a target. Which strategy users have doesn't affect our technique here, but of course an object-oriented technique has the advantage that there's that the attention is maintained on the object of interest. For the head-attached menu, we are relying on natural EyeHat coordination. So whenever we fixate an object with our gaze and then move our heads, VOR movement naturally holds our gaze in place. That's what happens when we look at each other and nod our heads. That's what stabilizes our gaze on targets. However, it is arguable that when we use explicit head shifts, where we ask users to perform a gesture while keeping their gaze, that's still seen as not quite as natural because most head shifts are led by eye gaze to a new target. So that might be a factor, but we don't know that, but might be a factor in why the EyeHat condition didn't do quite as well as the eye-hand condition. Head and hand differ in other ways, of course, also, and also in the implementation of the menus we had here. So it's worth looking at the design implications here. So the head-attached menu is interesting because it affords stable control. The head sits nice and stable on our neck, whereas with the arm and so on, we have other issues, gorilla arm and so on. And selections are possible with relatively small movements, small rotations of the head, which isn't much effort. So, so the head method also affords hands-free control, of course, and is interesting for systems that might not track hand movement at all. The hand-based version, on the other hand, affords more flexible menu movement, and in particular also to move the menu completely out of the field of view, which can be significant to avoid distraction, and in some ways it's also a more familiar technique. However, it involves more effort and it's more fatiguing. All these issues can also be addressed with other menu design strategies, for example, making menus contextual so that they don't always sit in the field of view and to avoid that they need to be actively moved out of the way. Other limitations, there are, of course, as in 3D interactions, so often there are depth issues. It causes issues when the menu is not at the same depth as the target, the accommodation problem, of course, but there's also the specific problem here of binocular disparity. Yeah? So if the menu is closer to the eye and further away from the target, we have it's not clear sort of is the alignment performed with the right eye, with the left eye, or with both eyes, and that is a possible source of error. Can be avoided, of course, by adjusting depth of the menu to bring it close to the target. I'm running out of time, I guess, but just a quick look at a few more application examples. Here we have a larger target object, and it becomes more obvious how gaze is important here to distinguish which tool is being applied over the object. And here's an example to show that we can extend the interaction to scalar input, yeah, and also to 2D input here to control mood and brightness of a light. I conclude with 3 takeaway messages. One, that EyeSeeThrough is an effective object manipulation technique that uses gaze as primary pointer, supported by either head or hand movement. The second takeaway point here is that visual alignment for selection is faster than 2-step target acquisition by gaze, and that may also be interesting for other types of application, generalizing beyond menu operation. And the final point here is that although the hand was preferred over the head, it's important to understand that both offer different affordances for interaction and application. Thank you very much.
We have time for one question, maybe, because people are leaving for other talks.
Hi, it's very interesting work. What I wanted to ask is, have you tried to make this interaction without the visible reticle of the gaze, because this can be very annoying for the user.
There is no visible reticle. That's in here to show you where the gaze is. Yeah.
Okay, great. Thank you very much.
Thank you very much. Thank you for coming to the talks. See you at the next session.